Hello, Chem students. We're going to start the second lecture on Chapter 2, Physical Properties, Polarity, and Types of Bonding. So we'll finish it off with this lecture. What we're going to discuss now are dipole-dipole interactions. These are molecules that have a permanent polarity built into them with a partial positive and a partial negative charge that gives them an attraction for each other that's stronger than, say, just the dispersion forces that we talked about earlier. Okay, and what we're going to use to look at the attraction for the molecules among themselves will be the boiling point. Because remember, when we go from a liquid to a solid, we separate the molecules by basically infinity. They don't see each other in the gas phase. And so we can measure the degree of attraction for each other by the amount of temperature that it takes to boil it. So we'll start off with two very similar looking examples. This first one is very nonpolar. We know that CH bonds are nonpolar and CC bonds are not polar. So this molecule, ethine, has a common name of acetylene, has a zero dipole moment, which is an indication of the degree of polarity. Because it has very weak attractions for its neighbors, the boiling point is very low. And in fact, the boiling point and melting point are essentially the same, and we call that sublimation. So very weak attractions. And if we look over here at this molecule, it looks very similar. There's an H with a C, SPH, and then an SP atom on the other side, but this time it's a nitrogen. So we know that the nitrogen is more electronegative and has a greater attraction for electrons. And also, you might remember back then we drew a resonance structure where we actually allowed the nitrogen to take two of the pi electrons to itself, and then we wrote a minus charge and a plus charge. So this reinforced the polarity that we see in something like this molecule, which is hydrogen cyanide. Otherwise, the molecules look very similar. Okay. Now that little difference that we just mentioned right there forms a very large dipole moment of 2.98 debye. So around 3 debye from 0 debye because of the nitrogen being at the other end. And that causes a very great difference in the boiling point. This was minus 84. The boiling point of this is plus 26. So it's actually possible that on a cold day this could be a liquid. Okay, so hydrogen cyanide is not anything that you would want to play around with. It's a very deadly poison. But it is something that is useful. Okay, now both the molecules are very linear in shape, so we might expect the melting point to be a little bit high relative to other things, but they're pretty different here, so you can see that even the polarity affects the melting point. The difference between these two and the boiling point is 110 degrees centigrade, even though they're about the same size and about the same shape, just the drastically different polarities, and that's why dipole-dipole interactions are so important to be aware of. Okay, so let's take a look at another one. What we're going to do is we're going to come down here and replace this H with a CH3. Excuse me. Now in organic chemistry, we sometimes just generalize this as an R group. So this is a methyl, but an ethyl or propyl or something else that's very simple, we could just call R, and they would sort of generically be similar. Now when we do that, something very surprising happens. The dipole moment goes from about 0 to about 0.8. That's remarkable, since we're thinking that there's no polarity in this carbon-carbon bond. But what this tells us is that something happened here. There is an imbalance of charge, and it's because of these two atoms being different. This is sp hybridized, this is sp3 hybridized. Now at this point we don't really know what that is, but we have introduced polarity, so it could be that the methyl is donating electrons towards this end and making this more negative on this end, or it could be that the methyl is pulling electrons to itself and being more negative, and then the other end's more positive. Just looking at this example, we don't really know. Okay, but we do know that there's more polarity. Look at what happens to the boiling point too. Okay, so that's partly increased dispersion forces because we have an extra carbon there, but it's also a tiny bit of the polarity that's we see there. Now let's do the same thing over here. Let's replace this H with a methyl. Oops, here it is. And when we replace this H with a methyl, we should be able to answer our question that we had over here. So if in fact the carbon-carbon triple bond here is more negative, then, and that's electronegative and pulling the electron density to itself, that should be accentuated in this one right here, because we actually have a nitrogen as well as the methyl. So the dipole moment should tell us what the answer is. Again, we can write the resonance form where we make the carbon positive. And if this methyl's helping that by donating electrons in and helping it pull the electrons away, whereas up here all we had was a hydrogen, then this should become more polar. More polar should be a bigger dipole moment. It's already pretty big up here, about 3. Let's see what happens. Now it's almost about 4. So in fact, it looks like that the methyl made this easier to put a partial positive here, made it easier for this nitrogen to pull electrons away because the methyl was donating in to help the positive that we have here. So that's what we call an inductive effect. Okay, an inductive effect is electron donation or electron withdrawal through a sigma bond. And in this case, our groups that we're talking about here are inductively donating. Okay, and the sp atoms that we have over here are withdrawing in terms of electron density. Okay, and you can see the boiling point goes up quite a bit again. So the boiling point difference here is about 104 from minus 23 to plus 81. So this is actually quite high boiling. This is acetonitrile. Common name would be ethane nitrile. Common name would be acetonitrile. Proper name is ethane nitrile. Now, if we wanted to kind of test this idea, we could switch the atom that we have here for something that we know, say, is electron withdrawing, and see if a predictable change occurs. So if I put something here that's electron withdrawing, I'm thinking that should pull back on the carbon-nitrogen triple bond, and the dipole moment should go down, should be less. So let's take a look. And sure enough, if we put a chlorine there, we know chlorine's electronegative, and if we pull electron density away, what's going to happen? Dipole moment drops off dramatically. So if we come over here, the dipole moment drops off from the carbon-carbon example. Okay. So that would imply that the chlorine is better able to compete against the carbon-carbon triple bond than the methyl. The methyl's donating in, the chlorine's withdrawing out, back out. Let's look at a double bond, see if we can translate this into more general cases. Now, if I have a carbon-carbon double bond with all hydrogens, that's completely balanced, no polarity, 0 dipole moment. We expect a very low boiling point. The only thing holding this close to its neighbors would be dispersion forces, and it is very low, minus 104. Okay. Now, if we come over and put an oxygen on the other end, we're thinking oxygen should be electron withdrawing. We should have a polarity introduced here, and in fact, we could write a resonance structure where we push the electrons up to the oxygen and have an O- and a carbon plus. So this is not as good as the neutral structure. We lost the bond, we have incomplete octets, but it's compatible with the polarities, so we allow this as a reasonable resonance structure. And you can see what happened to the polarity. It went from 0 to 2.3 divide. So it's quite a bit polar, all right, very polar. And you can see what happened to the boiling point, minus 104 to minus 20. So about 80 degrees different. Okay. So let's see if what we did before is going to be the case. We're going to take this guy and put it down here, and then we're going to change it in some predictable ways that try and introduce this idea of inductive effect. So what I'm going to do is I'm going to take away an H here, and I'm going to put a methyl, which we could say is an R group. Now, what we just saw is that the methyl donates in and allows the oxygen to steal more electron density away, and if that's the case, we should get more polar, and that should be a greater dipole moment. Okay, and that's exactly what happened. So you can see when I write this second resonance structure, this is a very electron-poor carbon because of the oxygen, but the R group here, the methyl group, is helping it out so that the oxygen can steal a little more electron density away. And we can see that in the increased polarity from the dipole moment. We still have one more spot over here, so we could do it again. And if this is truly the case, maybe the dipole moment will go up again. Okay, so if I put in 2 methyls, or 2 R groups, we do in fact see that the dipole moment goes up to 2.9. So it appears that these methyl groups which in more general cases R groups, are inductively donating through sigma bonds, and where there's an electron deficient center, that's going to help stabilize that electron deficient center. Okay. So let's do a little problem here. What we're saying is that if we have a positive center, then inductive donation should help because we're donating electron density into something that is a little bit positive. If we had a negative center, then inductive donation into the negative center should not help. That should destabilize. It should be less stable. We could turn that around. If we had a positive center and we have something that's inductively withdrawing, stealing electrons away, that should make it less stable because it needs more electrons. But if we have something with too much negative charge, okay, sort of a negative center, and we put something that can pull some of that away, that should make it more stable. Okay, so this is sort of a general idea of something that's very important in organic and biochemistry, and that is the idea of inductive effect. So let's take a look at a problem here. So in this first case, we have an H, and we have sort of a partial negative center, sort of like this here. And then we're going to substitute that H with an R group, say like the methyl or an ethyl or something like that. So now what is that going to do to this partial negative here? Will it make it better, more stable, or make it worse, less stable, or basically no change at all? Okay. So what you think about that. Now the R group's inductively donating. We're adding more electron density to something that's already too negative, so that should make it worse. That should destabilize. And what if I had something that was partial positive, and I have an H, and then I want to see what does an R group do if I have a partial positive here? Should it make it better? Should it make it worse, or no difference? So again, this doesn't have enough electron density. The R group's going to donate in and help it out, so that should make it better. Okay, so hopefully you got the basic idea here, because we're going to see the inductive effect all throughout organic chemistry. And if you go to biochemistry, it's there too. Okay, a few more examples. So here I have ethane, I have ethene, and I have ethine. So common names would be ethylene here and acetylene here. But all these are perfectly balanced. Okay, first off, each of the bonds really has no polarity, but even if they did, they're all balanced at all particular angles. So everything is, whatever the difference is here, it's opposed by this. Whatever the difference is here, it's opposed by this. But really, we're saying there's no polarity in these bonds. And since the only thing holding these two carbons to their neighbors is dispersion forces, same here, we expect pretty low boiling points. And they are. This is about minus 90, about minus 100, about minus 80 or so. So they all are very, very low. Now, what we did before was we replaced one of these H's with an R group. And again, I have a methyl group here. And so what does that do to the polarity? We're thinking it should do nothing to the polarity here. Okay, this molecule looks like it doesn't have any polar bonds, and that's the case. But I have sp3 connected to sp3. Very, very tiny dipole, about 0.1 or so. Okay, so it hardly affects it at all. We expected it wouldn't affect it at all, but there is a tiny little effect. If I come along here, put a methyl group, we just said that methyl groups are inductively donating, and now I have a double bond. So it turns out that this actually introduces a dipole moment, because a double bond is electron withdrawing. The sp2 carbon is a little more electronegative than the sp3 carbon. Okay, and so it introduces about 0.4 dipole, which is surprising at first. And then if we came over here to the triple bond, the sp carbon is even more electronegative than the sp2 carbon, which is more electronegative than the sp3 carbon. And so in this case, the dipole moment goes up actually a little more, 0.8, which again is very surprising, because this looks like it should be a molecule with no dipole moment at all, except for that fact. All right. So now we know on atoms that electronegativity increases with fluorine, and it's a little less with oxygen, and a little less with nitrogen, and a little less with carbon. So as you go across a row, the electronegativity gets higher and higher to the right. And it turns out that that's the case of hybrid orbitals too. So if we come up and look at the S and the P, remember we combine these to make hybrid orbitals. And if you look at the S, We filled in the s before the p's because the s electrons are held tighter. That's kind of like what we say when we look at a fluorine. The electrons around fluorine are held tighter because of its Z effective. Here, the electrons are held tighter because there's more percent S. So if I look at an sp orbital, that's 50% S, 50% P. So the greater percent S, the tighter the electrons are going to be held. Okay, so that's going to make it sort of like it's a little more electronegative. If I look at an sp2, that's 1/3 S, so that's 33% S. And if I look at sp3, that's only 25% S. Okay, so these are the hybrid orbitals that we see in organic chemistry. It doesn't really make any difference which atom you're talking about. Carbon, nitrogen, oxygen, whichever one it is. The more percent S you have, the more electronegative that orbital will be. Okay, so this is kind of a subtle thing. We're going to come back and see this in acid-base chemistry. We'll see this all over again. Now our next type of bond is going to be a hydrogen bond. These are extremely important, especially in biochemistry, but organic chemistry as well. And really it's just a dipole-dipole interaction, but it's so special that it gets its own name. We call it hydrogen bond. Okay, so for this to actually be the case, we have to have a hydrogen that's bonded to a very electronegative atom that can produce a charge separation here, so that we have a partial negative, and a partial positive. And that would be possible with OH, and that would be possible with NH. We would expect OH to have a larger polarity because oxygen's more electronegative, and that's the case. So in fact, in our course, we'll mainly just focus on the OH example. But if you were in biochemistry, NH would also be very important too, because of DNA, RNA, proteins, and things like that. Okay, so now what we're looking at here is we'll start off with water, because water is the premier example. So water has an OH on each bond here. They're both highly polarized. The oxygen's negative. It also has lone pairs that can interact with an atom from another molecule. So with a water molecule, the hydrogen could interact with a lone pair in another water. The lone pair could interact with a hydrogen. This hydrogen could interact with a lone pair. This lone pair could interact with a hydrogen. So in fact, a water molecule could be surrounded on 4 sides by other water molecules, and it makes for a very strong interaction, which is why water boils at a very high temperature of about 100 degrees. Okay, so that's a special property of water, but anything that has an OH will be able to do this. An alcohol, carboxylic acids can do it sort of in 2 places, because the carbonyl on one can interact with the OH on the other, and the OH on that one can interact with the carbonyl on the other. So you actually get sort of a doubling up of the hydrogen bonds on the carboxylic acid there. If you had any kind of a carbonyl and something in there that had a partial positive hydrogen, so here's like an H3O plus, that could interact strongly with a lone pair, so we get a strong interaction here. That's a hydrogen bond. Even an alkene, even a carbon-carbon pi bond with its electrons sticking out in space, can interact with a polarized hydrogen. Okay, so in this case I have it as HCl. So as I say up here, it could be NH, and here I show us HCl, although this is a unique molecule. There's no other way you could have an H on a Cl except for this. So there's other possibilities, but in our course it's mainly going to be OH that we look at. Okay, so it's not just, like I say here, it's not just another polar bond. The H has no electrons except those on the side of the atom that it's bonded to, and so it's reaching out to another atom to help get a little electron density back that this oxygen's is stealing right here, and that's the strength of the hydrogen bond. Okay, this shows the remarkable properties that happen when we have hydrogen bonding. So here I have the inert gases. Okay, we've already seen those before. We know the only forces of interaction for these guys are dispersion forces, and they're only one atom, and so the bigger the atom, the greater the dispersion forces, and what we see that translate into is a higher and higher boiling point. So the boiling point's minus 269, then it's minus 246, minus 185, minus 153. You can see that it goes higher and higher and higher. Okay, and that's because of greater dispersion forces. If we come all the way over to the other side here and look at carbon hydride, which is methane, and then silane, and germane, and stannane, if we look at all these guys, they all kind of look the same. The only difference is bigger and bigger atoms. Now, if we look at the difference in the electronegativity, 0.2, 0.2, 0.3, 0.3, we're saying that all of these molecules are nonpolar. There's no polarity. So the only thing holding one molecule to its neighbor would be dispersion forces. And as we just saw, if the atom gets bigger, then the dispersion forces should be larger and the boiling point should be higher. So if we look at the boiling points, it's exactly what happens, just according to our little model. Now, if we take this column right here, say the red column, that has water in it, which is so special. Now, if we come down at the bottom and look at the difference in the electronegativities, very tiny, 0.1. So we're saying this should be basically nonpolar. Okay, if I look here, it's 0.4. If I look here, it's 0.4. Remember, we didn't call it a polar bond unless it was greater than 0.4. 0.4 or equal to 0.4 or less, we said it was nonpolar. So these are all nonpolar, and we're thinking the highest boiling one should be the biggest one. That should be the hydrogen telluride. Okay, so if I come up here and look at the red, I see it is the highest boiling one. Okay, over hydrogen sulfide, over a hydrogen selenide, or hydrogen sulfide. Okay, and if we just followed that trend, we would come up to water and we'd say, okay, water should be, just keep the line going down like we did with methane, and it should be right about here, maybe minus 100. But in fact, we know that the boiling point of water is actually plus 100. So it's off the chart difference, 200 degrees different than we were predicting here. And that's because when we look at the polarity in the bond here, it's a highly polar OH bond, and that makes for very strong interactions with its neighbors, and that means we need a lot of energy to separate a water molecule from all the other water molecules. So that we have this great distortion right there that goes up. Now if we look at these other columns, say this column here with the nitrogen and this column here with the fluorine, the halogens, and the 5B group right here, the lower ones all have very small difference of electronegativity. We all say these are nonpolar molecules. And there's a little bit of polarity on the hydrogen halides, a little bit polarity showing up, so we might be a little bit suspicious on this one. But this one right here, it just goes down, 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 and then all of a sudden it shoots up to ammonia. And it turns out that even on this one right here, the main thing for the HI is the dispersion forces. Okay, there's a little bit of polarity here. Okay, but it still goes down, down. It's a little distorted because HCl has a little bit of polarity, but then it shoots up to HF. So HF, because of its hydrogen bonding, drastically is different than all the rest of the members of its family right here. Okay. So only dispersion on the sides here. This is dispersion and a little bit of polarity. This is all dispersion except at the top for water. This is all dispersion except at the top for ammonia. Okay. So this hydrogen bond, as I said before, is like really important bond here. The OH, the electrons are being stolen away from this hydrogen. That's the only electrons it has. It's just only has 2 electrons to be like the noble gas helium. So it's just sort of a naked proton here. And if there's a lone pair sitting out here, this guy can bury itself into that in a very strong way, such a strong interaction. So a good hydrogen bond might be worth about 7 kcals. Now you want to make a distinction. It's not the actual bond on the other side. Okay, this is about 110 kcals. So, but it is a very strong interaction for when you consider that we could have one at all 4 different places here. That could be 4 times 7 would be 28 kcals. So let's take a look at what happens to the properties in this case. In all of these first 3 examples, I have 4 second row atoms, but here they're all carbon. No polarity, okay? Very, very low dipole moment. Boiling point is 0 degrees. Now if I come along and introduce an OH, so I took away the carbon here, but I replaced it with an oxygen and an H, now I have the ability to hydrogen bond. Okay? And what happens is the boiling point goes from 0 to plus 97. So a huge increase because of that OH bond. Not surprising. Now if I went to the other end and I put another OH in place of the carbon at the other end, now I got 2 places I could hydrogen bond. I'm thinking it should go up some more, and it goes up a lot more. Okay, goes up 98 degrees Celsius because of that second hydrogen bond. So each of those hydrogen bonds, being OHs, increase the temperature dramatically. Now you might say, well, it's just the oxygen that's here. Okay, because I put an oxygen in, I'm going to have polar bonds, and maybe it's not the OH. So what I did was I took this formula right here, used an isomer of it, but I put the oxygen in between these two carbons, so this is an ether now. So there is no OH here, so what is that going to do to the boiling point? We're thinking if the OH is so important, the boiling point should go down. It goes down dramatically. So now the boiling point is like 7 degrees, whereas over here it was 97 degrees. So it dropped a lot, 90 degrees, even though they have the same molecular weight. Okay, you can see the melting point isn't that big a deal for either of them. So now let's compare these guys here. Remember, this was a very polar molecule because of the resonance we could push up to the oxygen, had a very strong dipole moment. So very strong dipole right here. Boiling point was about minus 19, minus 20, thereabouts. And then this is sort of the same formula almost. Okay, I have 2 extra hydrogens, but they're really nothing. Yet, when I look at this, the dipole moment is smaller. So I'm thinking, should that boil lower? And the answer is no, because I have an OH. So the OH can interact very strongly with its neighbors. One can interact with a lone pair, and this can interact with a lone pair from another molecule. And that makes it very hard to take this molecule out of the mix. When you boil it, remember, you're taking it away from all the neighbors. And so the boiling point is plus 65. That's a difference of 84. If we looked at ethanol, or acetaldehyde, remember when we put an R group here, it allowed us to be more polar. Okay, so we went from 2.3 to 2.7. The boiling point went up, probably partly because of dispersion forces. I got an extra carbon here, but this is a polar molecule. If I come over here to the OH, so pretty much the same structure, 2 carbons and an oxygen. So the dipole moment goes down. It's less polar because we're not reinforcing with resonance right here. But look what happens to the boiling point. Boiling point goes way up. I was at plus 20, but now I'm at plus 78. So this is ethanol, same kind of alcohol that you'd have in beer or wine or something like that. But you can see it has a pretty high boiling point because of that OH. Now, as before, if we replace the other H here with another R group, a methyl, it makes it more polar. And the boiling point goes up because we have an extra carbon in there. So boiling point goes up. That's not surprising. Now, if I look at the same carbon skeleton and put an OH instead of a double bond O, the polarity goes down because I don't have that second resonance structure reinforcing this polarity. But the boiling point goes way up because one of these bonds is an OH. Okay, so I go from plus 56 to plus 82, so the boiling point goes up. Here's another series. This is CH3F, CH3Cl, and so forth. So we're thinking this should be the most polar bond. But remember, the dipole moment was a little tricky because it had to do with the charge separation and the bond length. These guys are all plus 7 Z effective. Fluorine, chlorine, bromine, iodine. But the iodine bond is much, much longer because it has many shells of electrons compared to the fluorine, the HF. It only has 1 inner shell. Okay, the chlorine has 2 inner shells, the bromine has 3 inner shells, the iodine has 4 inner shells. And so that makes these electrons much more distortable, polarizable. And there is a little polarity, but in terms of the dipole moment, they're all about the same, very, very close to the same. When we look across, it looks like it's the dispersion forces that's deciding the boiling point, because CH3F is very low, because F is not distortable, holds on to its electrons too tightly. A little bit easier for chlorine, and so the boiling point goes up a little bit. A little bit easier for bromine, so the boiling point goes up a little bit. And then a little easier for iodine. So in fact, for CH3I, that's a liquid. Okay, these other guys are all gases. They actually used to use methyl bromide to fumigate strawberry fields and different agricultural fields because it could kill all the the microbes and the plant growth, I guess weeds and stuff. But they don't use that anymore since it's also a carcinogen. Now this is a typical problem you might see on an exam, where I sort of combine these guys to see if you can figure out the differences. So I list here 1, 2, 3, 4, 5 boiling points. And then I give you 1, 2, 3, 4, 5 different compounds. And so then you have to order them. So really you should be able to identify the exact order, the highest boiling, second, third, fourth, and fifth. I might just say, what's the highest boiling one? Okay, and then you would have to come up with that. But on an exam, you have to put them in order. So you have to do it all. So if I'm looking for the highest boiling one, I see polarity here. Okay, I see only dispersion forces here. I see an OH, that's going to be pretty strong interaction. And here I see ionic. This is going to be super strong, the strongest of any of them. And then I see no polarity. This is going to be dispersion forces. So if I look at B and E, they're both dispersion forces. The only difference is I got 5 carbons here, and I only have 4 carbons here. So the dispersion forces should be greater here. This should be higher boiling than this one. But they both should be pretty low. So we're thinking that's going to be these temperatures here. The easiest one of the whole bunch is going to be KCl, the ionic one. That should be very, very high. And we only have one that's very, very high. And so then I have a difference between these two that are both polar molecules, okay, but one of them has an OH. So I'm thinking the OH should boil higher than this one here, and that would be the 141 that goes with the carboxylic acid. And then the 80 would go with the ketone, butanol. Okay, we got a little bit more to do here, and that is we're going to look at solutions. So solutions are a combination of solutes, the things that are dissolved, and the solvents, the liquid in which they are dissolved. Okay, so this is almost everything in life. The blood inside you is basically a solution. Now there's a general rule that people use, you might see it in your lab. It's called like dissolves like. So things that are similar tend to mix together easily, and things that are very different tend to not mix so well, say like oil and water. Right? Now solutes could be really simple. It could be like one particular thing. Say you put ethanol in water, so you pour yourself a little mixed drink or something. So it could be very simple. If you put sodium chloride in water, you would have 2 solutes, because you'd have the sodium ion and the chloride ions. So that would be kind of simple too, only 2 solutes. But then you can look at something like blood, and we don't even know. Blood has so many things in it. Thousands of different things are dissolved in the blood. And so that would be a very complicated solution with many, many types of solutes. Probably the most familiar solvent in our world is water. That's the solvent that everybody started off with. Although now in organic chemistry we have many, many, many solvents, many types that have good properties for things we need to do. But that's a little too complicated for our course for the first time through. But usually the solvent is the major component. Okay, that's what you got the most of. Now water is so important that sometimes, even if it's there in a tiny amount, they call it the solvent. Say like with sulfuric acid. Sulfuric acid, they actually refer to water as the solvent, even though it might only be 1%. Okay, now solution is the combination of these, of the solutes and the solvent. That would be the solution. Now you've all dissolved stuff in water, and maybe even other solvents too, in your chemistry career. But there's certain things we have to look at. Now, when we dissolve something, we have interactions of the solutes and the solutes with each other that we have to overcome, because we're separating these guys and putting a solvent in between. We also have interactions between the solvent and the solvent, because we're separating these guys and putting the solute in between. So we would like to know the forces of interaction in terms of their strength, and it's just like we've seen before. Ion-ion interactions are the strongest. The lattice energy is generally very, very large. Hydrogen bonds are about second. Dipole-dipoles are about third, and dispersion forces are generally fourth. That's sort of the order. And this is a cost you have to pay to separate both of these parts, the solute and the solvent. But what you get back is you get interactions between the solute and the solvent. So they're going to take the place of what was over here. And if these are stronger than what you came from, then the substance will dissolve. But if they're not, then it won't dissolve. Remember, we did sodium chloride and silver chloride. Okay, so here the interactions, strongest would be ion dipole, say like sodium chloride and water. Or hydrogen bonds, just like water or alcohol. Or dipole-dipole, so say the carbon-oxygen double bonds that we saw. Or dispersion forces, so that would be completely nonpolar, a molecule. So what you're doing is you're trying to balance where you start and where you end up in terms of deciding if something's soluble. And remember, the rule was like dissolves like. Now, as far as polar solvents go, we're going to introduce a little model here, and it's probably a little too complicated if you haven't had physics, but we're just going to introduce this idea of, normally this would be called a capacitor. So capacitor runs some charge from a battery to one plate, so you build up, say, negative charge on one plate. And on the other plate, you build up, you pull electrons away, you get a positive charge. And so it's depends on what you have in the middle here as to how easy that is. So the comparison point would be like a vacuum. There's nothing in here. Or air. Air is about the same. So we'll say that all we have is air in between those guys. And now if we can put something in there that can help delocalize the charge that's built up on these plates, it should make it easier to charge up these plates. And so that'll be the material that we put in between. Now there's an equation that we could look at where there's a bunch of terms, but the part that tells you how much work it takes is this little energy term right here. Okay, so with air, that's kind of like our reference point. We call that 1. If we were to put water in here, then it would be 1/78th the amount of energy. Okay, because water is very polar, and water can kind of dissipate the charge through its medium. Right, so water is a very, very good solvent for dissolving ions, where you have charge separation. Now, what we're going to do is we're going to say the solvent, in this case water, is polar if its dielectric constant is greater than 15. Well, water is 78, so definitely water is polar. We'll look at other organic solvents too. Or we'll say it's nonpolar if the dielectric constant is less than 15. So then it's not helping out the work very much, just some other smaller fraction of that. Now there's another way we have to divide up our solvents, and that's with the term protic and aprotic. So a protic solvent has a polarized hydrogen, and for us it'll just be on oxygen. It could also be NH, but we're just going to say it's oxygen. So if we have an OH, then that's going to be a protic solvent. And very many times protic solvents are also polar. Okay, so we have 4 possibilities. We could have polar protic, a polar aprotic, we could have nonpolar protic, or nonpolar aprotic. Those are the possibilities that we divide the solvents up into. Aprotic means there's no polarized proton. All right. So it's just a picture. This is just a picture of how water could help dissipate the charge in a plate. The oxygen could gather by the positive end, positive plate, and the hydrogens could gather by the negative plate. Now, when you put ions in water, water can solvate all possibilities. So if I have a plus charge, say like a sodium, then water will gather around the sodium, usually about 6 places, and interact with that to help stabilize that plus charge by itself. And on the opposite sense, the chloride, the anion over here, water will hydrogen bond to that all around it, probably about 6 places as well. Now what I did here was I made it more general. If this is an H, we're talking water, but if this is a carbon, we're talking an alcohol. Okay, but alcohols are basically like organic water. So, and for many cases, this works. Okay, so sodium chloride will dissolve in water. But remember, not everything. Silver chloride does not dissolve in water. Now, a polar aprotic solvent is going to have, remember, the dielectric is going to be greater than 15, so it's polar. So here's our acetonitrile again, ethane nitrile. It has a very partial negative end on this sp nitrogen here. Okay, so that should interact very strongly with any cations. And in fact, this interacts more strongly than water does. So there's actually more energy released by this interaction with acetonitrile. But on the other side, it's not so good, because water has a very partial positive hydrogen that interacts strongly with anions. But acetonitrile, the partial positive is a carbon buried inside the molecule. It can't really interact with the anions very well. So you might think, well, that's not so good because we can't dissolve the salt as well. But it actually turns out to be way better, because what it does is it relieves this anion of all the interactions with the solvent. And so it's relatively independent by itself, and it's available to react much more readily than is the case up here. When I was a student, this is the way we talked about these anions, because most of the solvents were like alcohols to get the ions to dissolve. Now we have many more modern solvents, and acetonitrile is a special good one, other ones too. And so now this is a better solvent when we want the anions to react. Okay. So I have several solvents here. Of course, there's many, many other solvents, but up here I have protic solvents. So water clearly has OH. Alcohols, OH, OH, OH. Carboxylic acid, here's methanoic acid called formic acid, has OH. And you can see they're all protic because of the OH, but they're all pretty polar too. The dielectrics of all these are greater than 15. So these are polar protic solvents. Now if I come down here, there's a lot of solvents that are pretty polar. Dimethyl sulfoxide, look, it has a dielectric of 46. So that's over here. Very polar because of the sulfur-oxygen bond. Okay, very polar. But you don't have any OH. Okay. So there's no OH that could hydrogen bond with something else. Okay, so we have polar aprotic solvents. We got lots of those. Here's the acetonitrile I just showed you. And there's a whole bunch of these, but we're not going to worry too much about it except to recognize it. And then down here I have solvents that are not very polar. They're all dielectric less than 15, and there's no OH. So these are just nonpolar solvents. So you might think that's not a good thing, but there's lots of molecules that react that are nonpolar. And so these types of solvents will help dissolve them. And think of cell membranes. Cell membranes are nonpolar, and they separate the inside of the cell from the outside of the cell. So actually having nonpolar environments is sort of a good thing. We want all the options possible. So we have something like diethyl ether or ethyl ethanoate. Okay, so here's ethyl ethanoate, here's diethyl ether, very low dielectrics. Right? So here's a couple of biochemistry places where hydrogen bonding is super important. Okay, you've all seen DNA and RNA bases, I'm sure, in your other classes, your biology classes. But the adenine and thymine bases have 2 places they can hydrogen bond, and the guanine and cytosine have 3 places where they can hydrogen bond. So you might guess that the interactions between these are going to be stronger than the interactions between these. And remember, when your cell duplicates, it has to unravel all of the DNA. Or if your cell's going to make some RNA that's going to make some protein, then you have to unravel that part of the DNA. If you have more GC interactions, it's a little harder to open that up than if you have AT interactions. Now, another place where hydrogen bonding is real important is in protein chains, because proteins have a lot of NH and double bond O's. And so they can arrange themselves different ways. This is what they call an alpha helix, where guys up higher interact with ones below, oxygens below, and make for hydrogen bonds. And then they have what's called beta-pleated sheets, where it sort of zigzags down in one direction and comes back the other direction. And these could either be parallel or non-parallel. But this isn't really our part of our course, except for the recognition of the hydrogen bonding that's possible. So I have here a very simple scheme for mixing, say, solutes and solvents. So I picked something that's ionic, and what could be easier than sodium chloride. So sodium chloride is something we're all familiar with. And then I picked 2 extremes of solvents. One is water, very polar, lots of OH, and one is nonpolar, something like, say, like octane that might be part of your gasoline. So that's a very nonpolar solvent. If you took sodium chloride and put it into water, which you probably have done, okay, there's going to be a big cost. Cost a tremendous amount of energy to separate these ions. But there's a big gain because each of the ions interacts very strongly with the water molecule, either the oxygen in or the hydrogen in. And so the balance overall, solvation energy is more important, and this dissolves. So like dissolves like. I have something that's ionic, the extreme of polarity, and then I have something that's very polar, the water molecule here. Now if I look at gasoline, gasoline has no polarity. So if I come over and try and separate these ions, what do I get back? I get nothing back. And so they're not going to separate, they're going to stay together. If you sprinkle salt into gasoline, it's just going to sink to the bottom. Okay, it is not going to mix because they're too different. Okay. So what's the cost? Dispersion forces here, they're weak. Okay. But up here, the lattice energy is huge. Okay. Now the other possibility would be we had something that's fairly nonpolar, say like wax, something that's sort of waxy, maybe a candle. Okay. And if we try to put that waxy substance into water, you've probably done this before, it just floats on top because it's less dense. The water costs too much energy to separate the water molecules with their hydrogen bonds, and we get nothing in return from the nonpolar solute. And so it doesn't mix. Whether it sinks or floats depends on the density. If this is less dense, it's going to float. If it's more dense, it's going to sink. Okay, so the big cost here is the hydrogen bonds. Now if I come down and I mix, say, this waxy substance with gasoline, say octane or something that's nonpolar, there's not a big cost here, dispersion forces. There's not a big cost here, dispersion forces. And so they should mix fairly well. Okay, doesn't mean it's going to mix instantly, but probably with a little time it will dissolve into solution because the cost is not great and the gain is not great, so the balance is there. Also, this is very disorganized, and entropy is always favored, greater entropy, disorganization. So here's sort of a little problem for you to think about. I'll go through and I'll ask you what you think for just a moment, and then we'll say what it is. We want to know, are these molecules hydrophilic, meaning they love water, or hydrophobic, meaning they fear water? Okay, they don't want to mix with water. This is extremely important in biochemistry because we want to keep everything organized. So our cells are highly compartmentalized with membranes to separate different molecules that would otherwise react very quickly with each other, and that would not allow for life to continue. So hydrophobic means it doesn't want to mix with water, and hydrophilic means it loves mixing with water. And remember our rule of like dissolves like. Okay, water has a lot of OH and is very polar. So if I look at a molecule like vitamin A, I'm looking, I go, oh wow, there's almost nothing that's polar. There is a little OH here, but look at the molecule. The molecule's over 95% nonpolar. So I'm thinking this is not going to be soluble in water. It should be hydrophobic. And we could also say it's fat-loving. Okay, fat cells have a lot of nonpolar stuff in their membranes. So this should be like cell membranes, but not like water. This molecule right here, vitamin B2, if you go up and down the line, OH, 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 nitrogen, NH, carbonyls, this looks to be pretty polar. Okay, so I'm going to say this is hydrophilic. Should be water soluble. Okay, and that's what it is. If we look at vitamin B6, it has a lot of OH, it has a plus charge, it has minus charge. This should be very soluble in water, but not soluble in nonpolar membranes. Okay, we even have ionic material here. If you look at ATP, that's loaded with polarity. OH, OH, NH2, and then all these phosphates with negative charge. This has got to be better in water than it is in a cell membrane. Okay, so this should be hydrophilic. If you look at vitamin C, also hydrophilic. Look at OH, 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 OH. Even these oxygens can hydrogen bond a little bit. And what do they tell you? They say if you take vitamin C, it just washes out every day because it's so water soluble. So you have to constantly be taking vitamin C to keep the levels up. If we look at vitamin D, various forms, this is vitamin D2. tons of nonpolar carbon, hydrogen, carbon, carbon bonds right here. Tiny little OH here, so I'm thinking, this is going to be hydrophobic. Doesn't really want to mix with water. It's like oil and water. If you look at vitamin E, looks very similar. We only have one little OH, and then everything's sort of hydrophobic. Tiny little oxygen here, but not enough to balance all this out. Okay? So, in fact, vitamin E loves being in your membrane, and it's good at blocking free radical damage. Vitamin C loves being in your blood, and it's good at blocking free radical membranes, free radicals in the body. And so together, these guys can work to help protect you against free radical damage. Our last example here is cholesterol, and if you look up above, it kind of looks like this one. Vitamin D2 kind of looks like this one. So in fact, cholesterol is hydrophobic. It loves being in membranes. It's a large part of many, many membranes in living organisms. Kind of gives it a rigidity and structure. But also, cholesterol is the source of all our steroids. So estrogen, testosterone, even vitamin D2 here. It's part of that. It actually generates that in many, many steps. So hydrophobic. Our last example right here takes cholesterol, which we just said is very hydrophobic. And in many steps, cholesterol is made into something here called a bile acid, like glycolate. And if you look at what happened, nature put OHs. First off, it took away this double bond, put a hydrogen here, and pushed this ring down. Okay, put some OHs on the bottom, over here and over here. Took this chain and took it from hydrophobic, added on this polarity, put an O minus here and an NH, like an hydrogen bond. Okay, this would be a glycine amino acid. And so if you look at the bottom part of this molecule, it's very, very polar. But if you look at the top part of this molecule, it's very, very nonpolar. So the thing that releases glycolate is your gallbladder, right after your stomach. So if you eat a lot of fat in a meal, then the gallbladder is going to release these bile acids. And what the bile acids will do is they'll put this face up to the fats so that they can solubilize them, and then they'll expose this part out to the blood where the water is. So it makes like a big old fat ball that carries your fat around and can drop it off at different places in your body. Okay, and then your body actually recycles a lot of this. So by the time it gets to the large intestines, it gets like pumped back into your bloodstream and goes back to the gallbladder. You can do it again. Okay, so that's pretty much the end of what we're going to talk about on this particular topic. Remember, we have the topic 2A, and this is topic 2B. And then we'll continue on in 3. 3, I'm going to actually have you guys look at all by yourself.